Hello everyone, welcome to Exploring version 14.3. We just have launched version 14.3 today. You can download it now for your computer, for Wolfram Desktop, or you can run it in the cloud, in Wolfram Cloud. So I just posted a blog about version 14.3. It's pretty long. Version 14.3 is a big release. We had our last release, version 14.2, January 23rd of this year. It's just over 6 months later, and now we are launching version 14.3. Even though it's a .x release, which sounds kind of modest, it's actually a very big release with lots of important and updated functionality, particularly in lots of core areas of the system. And I guess I should say that I'm particularly pleased to be able to report that in this release, we're delivering an unusually large number of very long requested features. You might ask, why didn't they come sooner? Well, the main problem is that they were hard, at least to build to our standards, and it's simply taken that long to get them to the point where we think we can release them. I think the longest wait for a feature is one that we had planned in version 1.0 38 years ago that's now finally being released in this version 14.3. So it's exciting to see that actually happen. I think we're pretty much done now with the version 1 to-do list, which is good 38 years later. Well, those who followed the live streams that we've done of design reviews for Wolfram Language will have seen lots of effort that we put into doing all of these designs, and I thank people who've contributed in these live streams. I think we've done about 42 hours of live streams since version 14.2, specifically related to language design. And it's, we've been putting in that kind of effort in language design now for, well, nearly 40 years. I think that's a sort of a unique thing in the software world to have put this kind of innovation and effort into a system consistently for that long a time. And also, I will say, to have maintained compatibility across all versions from version 1.0. It's at this point, we have a very big system, more than 7,000 built-in functions and so on. And sometimes even I forget some of the things that the system can actually do, which makes it very convenient that at the end of last year, we introduced our new notebook assistant, which is a thing that uses kind of AI technology together with a lot of our own computational technology to give you kind of suggestions about what to do. And the thing that works surprisingly well is to say something extremely vague to the notebook assistant, and it will generate a piece of precise Wolfram language code that may or may not be exactly what you want. But the good news with Wolfram language, unlike sort of low-level programming languages, is Wolfram language is intended for humans to read. And so it's something where once the notebook assistant has generated a piece of Wolfram language code, you can read it and you can say to yourself, is that what I wanted or not? If it's what you wanted, great. You use it, you can build this whole sort of tower of capability on top of it. It's not what you wanted, well, you tell notebook assistant, do something different, or you modify it yourself or whatever else. I think it's the whole story of kind of notebook assistant and the interaction of Wolfram language with AIs is something that has worked out beautifully. We designed Wolfram language over all these years to be as coherent and consistent for humans to use, and it turns out those are exactly the same kinds of things that AIs need to be able to make good use of Wolfram language as a tool. So it's been great to see that kind of synergy develop. And I think the big story at this point is Wolfram language is sort of this precise computational formalization of the world, and it interacts very nicely with kind of the linguistic interfaces that are provided by LLMs and so on. Together, one can do very great things. On their own, one can do great things with Wolfram language. But LLMs on their own can do many kinds of things, but they're different from the kinds of things that one can do well in a computational system. But together, one can do really, really smoothly a lot of kinds of things. Well, it's another consequence, actually, of the consistency of Wolfram language in terms of design is that it's very easy to build things on top of it. And it's very easy to have things where sort of the coherent design is the main part of the story, but then there's just this one extra piece, one extra function that you add that does a particular thing you need, that's something very specialized, or perhaps something quite experimental. That's the story of our function repository. And at this point, there are more than 3,200 functions in the function repository, which, by the way, the Notebook Assistant knows about. So when you ask it something, it will not only give you a kind of a solution for that in terms of pure Wolfram language, but also in terms of functions from the function repository, which kind of work well because they're so much based on this very tall tower that we built in Wolfram language itself. They're only adding that little extra piece for some particular function. They don't have to create some whole framework from scratch. The framework is already there and well designed. They're just adding one little piece. Well, okay, let's go back to version 14.3 and let me start trying to give you a bit of a demo here. So let's go ahead and concentrate on the computer here. So you can find much of what I'll talk about here is in this post that I just made a few minutes ago. And it's a long post with a lot of different sections. I'll be going through all of this here today. And then maybe there'll be time, depending on how long this goes, maybe there'll be time for some questions at the end. All right. Well, let's get to work here. So, you know, I started using computers with screens in 1976. And back then, every screen was black and the text on it was white. And in 1982, when workstation computers came out, it switched around and I started using displays that looked more like printed pages with black text on white backgrounds. And that was the usual way things worked for several decades. Then about 5 years ago, dark mode started to be popular. And one was back to kind of 1970s style displays, of course, now with full color at much higher resolution and so on. Well, we've had dark mode styles available in notebooks for a long time, but in version 14.3, we now have full support for dark mode. So if you switch your system to dark mode, version 14.3 will have all notebooks by default display in dark mode. But there's also a way to switch each individual notebook. I can say, use dark mode for this notebook, and now it's in dark mode. We can start typing 2 + 2 = 4, and so on. Well, you might think that it should be kind of trivial to set up dark mode. I mean, don't you just have to change the background to black, text to white, and so on? Actually, there's a lot more to it. In the end, it's a pretty complex user interface and algorithmic challenge that I think we've actually solved really nicely now in version 14.3. So here's a very basic question. What should happen to a plot when you go to dark mode? You might want the axes to flip to white, but you might want the curves to keep their colors. Otherwise, if you had text that referred to those curves by color, how would that work? Well, so in version 14.3, let's see what happens with this plot. There's the plot in dark mode, and you can see the axes flip to white. If I flip back here to light mode here, you'll see the axes switch to black, but the colors of the curves have been chosen so that they work both in light mode and dark mode. So that's sort of the beginning of the story. We've actually spiffed up, in version 14.2, we spiffed up a bunch of default colors for plots. And we did that in part precisely in anticipation of being able to support dark mode in version 14.3. So, well, lots of tricky cases. Let me give you another example here. Here's a 3D array plot, and there it is looking very lovely in dark mode here. And also, I hope, looking similarly lovely in light mode? Well, graphics generated by computation aren't the only kind of thing affected by dark mode. There are also, for example, endless user interface elements that all have to be adapted to look good in dark mode. Actually, in all, there are thousands of colors affected, all needing to be dealt with in a consistent and aesthetic way. So to do this, we ended up inventing a whole range of methods and algorithms, which I guess will eventually make externally available as a packlet. But the result is that a notebook can essentially automatically, any notebook you've created can essentially automatically be configured to work in dark mode. So what's happening underneath? So needless to say, there's a symbolic representation that's involved. Normally, you would specify a color like red by just by something like this. But in version 14.3, there's kind of a new construct, which is the wrapper light-dark switched. So here we have this thing which by default will show both its light mode and dark mode versions. If we switch now to dark mode, then we will see that the light blue has come out on top. The light blue is what will be used if we gave that color as the color of a curve in a plot, for example. That will be the color, light blue will be the color used in dark mode, red will be the color used in light mode. So for example, here's an example of that. If I say text, the word text, 25-point text, in dark mode, this is light dark switch. So in dark mode, it's pink. In light mode here, it is red. So that's sort of a typical case of this kind of thing. So if you just say light dark switched of red, then it will look in light mode like that. In dark mode, it will automatically pick an appropriate color to use that will work in dark mode. So as an example, we can also do the following. We could say something like this, where we're saying, let's see here, where we say we want to make the light mode automatic. The dark mode is yellow. Now the question is, what will this be in light mode? Because yellow on white isn't very nice. Let's see what it does in light mode. Well, in light mode, it turned the yellow into that grayish color so that it's visible on the white background. Well, what if you don't want to explicitly insert light dark switched around every color you're using? For example, say you already have a large code base full of colors. Well, then you can use a new style option, light dark auto color rules, to specify more globally how you want to switch colors, if you don't want to just use the default in switching colors. So let's see, this for example, this will show you, this should show you to make a style that is a red disk and a blue disk, but have these listed colors, in this case just blue, be ones that will be light dark switched. So if we go here and we go to dark mode, the red will stay exactly the same as it was before, but the blue will switch because it's in the light dark auto color rules as a listed color to switch. So an alternative here is that you could use light dark color rules goes to all, in which case it will automatically switch all colors. There we go. It's switching all colors to in dark mode. Automatically we switch back to light mode here. We'll see those two colors both switch back to their explicit reds and blues. So for example, there's a convenient setting, light dark auto color rules to non-plot colors, which says to do automatic switching, but only for colors that aren't our default plot colors, which, by the way, are colors that have been set up to work well in both light and dark mode. Well, the there are all sorts of subtleties. So in version 14.3, we updated many functions to produce light dark switched colors. But if those colors were stored in a notebook using light dark switched, then if you took that notebook and tried to view it with an earlier version, those colors wouldn't show up at all because the earlier version doesn't know about light dark switched. We actually quietly introduced light dark switched in version 14.2. So you can take a version 14.3 notebook and run it, and it will work just fine in version 14.2, even if it has light dark switched in the initially version 14.3 notebook. So going back at least 6 months, there's complete compatibility of any notebook. But if you have light dark switched, then that's not a color, that's not a thing that will be understood in earlier versions because we hadn't thought of it yet when we built those earlier versions. So how do we deal with backward compatibility for light dark switched colors that our own functions produce in version 14.3? We want it to be the case that you can take a 14.3 notebook and run it at least a decent number of versions back beyond just the 14.2 case. Well, the way we've done this is we don't actually store these light dark switched colors, the default ones, in notebook expressions using the light dark switched symbolic wrapper. Instead, we're doing something kind of tricky. We're storing the colors in ordinary RGB color form so that they can be interpreted in earlier versions, but the RGB values are numbers that have their switched versions stenographically encoded in high order digits. So it's kind of a trick that, it looks like a red, but it isn't precisely RGB color of 100. It won't be precisely red anyway. These are colors that are our default colors that are more complicated choices of color. But in earlier versions, it will just look like a color that was chosen. But in version 14.3, we can recognize the steganographic pattern of bits in the number, and we can recognize that this is actually a light dark switched color, and we can pull out the switched version of that color. So we've gone to lots of trouble to handle dark mode within notebooks. But operating systems also have ways of handling dark mode. Sometimes you just want to have colors that follow the ones in your operating system. So in 14.3, we've added the function system color to be able to do that. And let's see, we can use that here. So this will now say, I want this text to be in the system color that is used on, I happen to be using a Mac, that is used on my Mac for tooltips. And that system color is gray. But if we now switch this to dark mode, we'll see that that system color now turns into a different color. That different color there is the system color that is used for tooltips in dark mode. So, okay, let's talk about how textual content in notebooks is handled in dark mode. So, black text is obviously rendered in white in dark mode. But what about things like section headings? Well, let's try doing a section heading. That's a slightly different color in dark mode than it is in light mode. All of those colors have been chosen to work in. They've been chosen to work in each of these modes. Or something like entities. So for example, let's say we have the entity Earth. In light mode, that will be a yellow box. In dark mode, it's been recolored to look good in a dark mode notebook. Okay, so all these things like entities, section headings, and so on, these use different colors in light and dark mode. And you might ask, well, what if I want to kind of copy those colors? If I want my notebook to look good in something to look good in light and dark mode, and I just want to make it consistent with the colors that are used in the system. Well, we have introduced a new concept, theme color. Actually, we introduced it in 14.2, but it's part of a whole framework that we're building out in successive versions. But the idea is that theme color allows you to access theme colors associated with particular themes. So, for example, there might be something like the accent 3 theme, and that's saying that make this text in the accent 3 theme color. And for example, accent 1 with a particular blend of accent 1 is the color that is used for section headings. Accent 3 is used for different things, and so on. But you can pick up these different accent colors from theme color to use in your own programs to make them look consistent with the coloring that's used in notebooks in either light or dark mode. So if you want to, as I say, you can switch between light and dark mode will be switched between automatically. If you switch your operating system to dark mode, all Wolfram notebooks will automatically switch by default to dark mode. But the thing I've been doing here is clicking this moon sun icon up here that switches between light and dark mode explicitly in a particular notebook. So it's an interesting question for me. I've been using light mode for so long that it's the only thing that really feels natural. But maybe for this exploration, why don't I use dark mode and see whether in just a short time here, I'll overcome my habits of 25 years and feel I should go back to the dark side again, so to speak. All right, that was the first thing. It's been a long requested feature to have dark mode in notebooks. I think we've implemented dark mode really, really nicely here. And I was just showing you some of the features it has. All right, let's turn to a different area, modern times. Let's talk about AI. So how does all the stuff we're doing relate to AI? How does it sort of connect with the modern agentic world? I mean, in some ways, the whole story of the Wolfram language is about, quotes, AI. It's about automating as much as possible. So you as a human just have to say what you want, and then the system has a whole tower of automation that executes it for you. Of course, the big idea of the Wolfram language is provide the best way to say what you want, the best way to formalize your thoughts in computational terms, both so you can understand them better and so your computer can go as far as it needs to work them out. So modern sort of post-ChatGPT AI has been particularly important in adding sort of a thicker linguistic interface layer for all this. And in Wolfram Alpha, we kind of pioneered natural language understanding as a front end to computation. Modern LLMs extend that to let you have whole conversations in natural language. So I've talked about this a lot at other times, but what LLMs are good at is rather different from what the Wolfram language is good at. I mean, at some level, LLMs can do the kinds of things unaided brains can also do, albeit on a larger scale, faster, and so on. But when it comes to raw computation and precise knowledge, that's not what LLMs or brains do well. But of course, we know a very good solution to that. Just have the LLM use Wolfram language and Wolfram Alpha as a tool. And indeed, within a few months of the release of ChatGPT, we'd set up ways to let LLMs call our technology as a tool. Well, we've been developing ever better ways to have that happen. And indeed, actually, we're just working on a big release in that area that'll be ready fairly soon. But it's popular these days to talk about AI agents that just go off and do useful things. At some level, the Wolfram language and Wolfram Alpha can be thought of as universal agents, able to do sort of the full range of computational things, as well as having connectors to an immense number of external systems in the world. Yeah, Wolfram language can send email, browse web pages, and actuate lots of other things in the world. And it's been able to do these things for decades. And if one builds the core of an agent out of LLMs, the Wolfram language and Wolfram Alpha serve as universal tools that the LLMs can call on. So although LLMs and the Wolfram language do very different kinds of things, we've been progressively building more elaborate ways for them to interact and for one to be able to get the best from each of them. So back in mid-2023, we introduced LLM function as a way to call LLMs from within the Wolfram language. Then we introduced LLM tool as a way to define Wolfram language tools that LLMs can call. And in version 14.3 now, we have another level of this integration, what we call LLM graph. So the goal of LLM graph is to let you define an agentic workflow directly in Wolfram language, specifying a kind of plan graph whose nodes can either give LLM prompts or Wolfram language code to run. So in effect, LLM graph is a generalization of our existing LLM functions with additional features like the ability to run different parts in parallel and so on. So here's a simple example. Let's do this. This is an LLM graph that has just two nodes. So I think I can make it bigger there. Yes, it has just two nodes, and which can be executed in parallel, one generating a haiku and one generating a limerick. So we can apply this LLM graph to a single input. So for example, we can apply it to the input blue wolf, and now it will run blue wolf with our haiku prompt and our limerick prompt. It'll give the result in a data set. And we'll see what we get. All kinds of weird stuff. Okay. So this was a very simple LLM graph that in parallel called an LLM twice, once for a haiku, once for a limerick. Okay. So let's do something a bit more elaborate. So let's do this. Let's make an LLM graph that is a workflow for summarizing text that starts up by breaking the text into chunks using a Wolfram language function, this function here, string partition, breaks them into chunks, then runs LLM functions in parallel to do the summarizing. So it's running a listable LLM function here to summarize in parallel these chunks, the result from make chunks, and then runs another LLM function to make a single summary from all the chunk from all the chunk summaries. So we can visualize this information, visualizes this graph. So it's starting with our text, it's making chunks, it's summarizing the chunks, then it's combining the summaries. Okay, so let's now apply our summarize function, LLM graph, to the US Constitution. Okay, so it's going to crunch away for a while. Hopefully, okay, there's its summary for the day. I'm sure if we ran it again, it would give a different summary, but it's summary of the US Constitution based on breaking it into chunks, summarizing each chunk, and then combining those summaries. Okay, so an important feature of LLM graph is that it allows one to support test functions, which are nodes in the graph that do tests that determine whether another node needs to be run or not. So the prompts here are a bit verbose, but let's just run this and let's visualize that. Go ahead here, visualize it. So this is some kind of corrector that is deciding whether to reviewing things, it's deciding whether to rewrite things, and then giving it final versions. So for example, let's run the corrector on 2 + 2 = 4. Yep, it thinks that's correct, so it's all good. And now let's run it on 2 + 2 = 5. Okay, here, it's going to run the decider node, the review node. What's it doing? It's rewriting. Okay, so now it says the incorrect input is there and it's been rewritten as this. And that was achieved by this, essentially, you can think of it as an agentic workflow encoded by this LLM graph here. So this is sort of a style of programming. It's a way of making sort of arbitrarily sophisticated programs that are kind of interwoven with LLM functionality. And it's kind of allowing one to build arbitrary agents within Wolfram language that mix the capabilities of the computational capabilities, knowledge capabilities, precision, and so on of Wolfram language together with the kind of the things that LLMs can do well, and they can be interwoven. And in fact, we're using exactly this technology for a bunch of things that we're building that can be again, sort of do further integration of the kind of modern AI world and the quotes traditional, I still think it's an artifact from the future, Wolfram language, computational language world. All right, so that's a little bit in that AI direction. Let's move on, talk about some more things that are in version 14.3. People have only been asking about agentic workflows for a few months, so that's not one of our long-running long requests. But let's come to something which is a long-running request, which is putting fits into plots. And so let's take a look at something like this. We are taking, this is an example of, actually it's a tabular example. We made a plot. Here's the result. But we might say, well, I want to put some kind of fit line. I want to indicate sort of a fit line through here. Maybe a bunch of these points are on top of each other. We can't really tell how many of them there are there. What roughly is the fit to this? Well, there's a new function, list fit plot, which makes a list plot and adds a fit line through that list plot. By default, it's adding a local fit line, which means it's sort of tracking locally the data. But we can also ask it to sort of globally make a fit with some particular form. So for example, if I say plot fit is linear, here it will insist on making a linear fit to that data. Or for instance, I could do an exponential fit instead. And now it'll make an exponential fit to that data. Okay, well, here all we're doing is to plot the original data along with the fit line. And but there are other things we can do as well. So for example, here we're telling it to, we're using plot fit elements. We're saying both plot the data points and band curves. These are the 95% and so on bands around that data. Okay, so this is how one can now very conveniently visualize fits in Wolfram language. What about finding out what the fit actually was? Well, we've had functions for doing that for a long time, linear model fit, nonlinear model fit, and so on. But in version 14.3, there's also the new local model fit. So let me show you how that works. So local model fit takes some data and it gives a fitted model, just like linear model fit would do. It gives a fitted model, but this fitted model object is something which, if we plot it, we will get that interpolated data line that is a local fit to the data, as opposed to doing, I think we might be able to do here, linear model fit. Oops, I gave the wrong kind of data there. Well, no matter. We're working on a lot of new functionality for fitting that will fit, not to make a pun, all this stuff together really nicely. That'll be coming in future versions. So local model fit is a non-parametric fitting function that works by doing local polynomial regressions, loss, LOE, SS type fits. Another new function in version 14.3 is kernel model fit, which fits to sums of basis function kernels. So for example, here we can say there's a kernel model fit, same data, and that you can see it wiggling a lot more. You can ask for all kinds of detail in here. So for instance, this is asking for a Cauchy kernel with width I think that's width 100. I don't think that's width 10. I think if we change that, that would be width 10. Yes, with width 100. So, okay, what we plotted here is a best fit curve using this kind of kernel fit. Whenever we get a fitted model in version 14.3, we can not only ask for the best fit, but also for things like fits with errors represented by around objects. So here we can say locomotive fit, and this will give us a best fit around. It'll give us this approximate around number here. So we can also do something like plot the best fit around as a function of a parameter, and there we'll see this band of fits with this sort of statistical uncertainty. You can also show band curves not for the fit. That's the band curves for the fit, but for the original data. Here are the band curves for the original data. So list fit plot is specifically set up to generate plots that show fits. And you can get those plots by first explicitly finding fits, then plotting them. But there's also another way to get plots that include fits, and that's by including the option plot fit in ordinary plotting functions. It's the very same plot fit function that you can use in list fit plot to specify the type of fit to use. But in a function like list plot itself, plot fit simply specifies to add a fit, in this case, a linear fit. So you can do things like this. We can say something like do a list line plot. And here it's putting a line through data, but now it's doing that by using not this kind of linear interpolation, but instead local interpolation specified this way. So we can also do fits, of course, in 3D. So here's some data, and this is now showing, this is a list fit plot 3D, where that surface is showing the 3D fit to those blue data points. And we can also, if we want to be even more elaborate, we can put band surfaces into this. So now we're showing both the data and 95% bands for the fit around that. So we can also use functions like list contour plot also allow fits. So this is a regular list contour plot. It's kind of scratchy. But now we can say here, we can take this list contour plot and we can say plot fit to automatic. And now it will automatically do a local fit and produce a much smoother contour plot. Of course, and this was an issue that came up already in version 1, we decided not to automatically smooth curves because we want to plot the data as the data is. But if you explicitly say plot fit to automatic, for example, then you're asking for something which is a not the real data plot, and that's what you're getting here. All right, let's move on. So the next thing we've done in version 14.3 is upgrading our maps. And we've upgraded the default rendering for maps. So for example, geographics, default geographics will now get, I'm surprised that progress monitor showed up as white here. I'm surprised that doesn't show up as a different color in the dark mode. But anyway, there it is. It just was up for a moment. So this is now our default view of the world. And needless to say, it's set up so that it looks good both in light mode, and both in dark mode and in light mode. and works the same in both cases. So what happens what you can see here, that there's sort of terrain that's shown in the big Earth, the full Earth. As we go down to smaller scales, like let's say we just plot a single country, for example, we'll start to see the terrain fade out. So we can start to see the labels here. The terrain is not as dramatic as it was before. And if we go to a still smaller scale, we can, let's look at this. If we go to a still smaller scale, the terrain will almost completely fade out, and we'll be able to start seeing roads and things like that. By the way, this I think looks different in light mode. Let's take a look at that. In light mode, oh no, that's very odd. Oh, I think if we render this, is that right? What's going to happen? Yes, if we render this in light mode, then it will show up in a different way here. This is okay. So let's zoom in again, and we'll start seeing yet more fading of kind of the terrain in favor of the actual structures and roads and so on that we see. So we've done a whole bunch of work on really making these maps look as nice as possible. And we can, if we want to, we can use satellite image instead as the background. There it is. There it is. All of these different things have dark mode. So if we switch to dark mode here, we can re-render this now in dark mode. I think the satellite image is going to look pretty much the same in dark mode. One of the things about these maps now is that they're all resolution dependent. They're all full resolution. You can make them as big as you want. They're all made with vector graphics. So this is a capability that we introduced as an option in version, actually long ago, in version 12.2. But by now, we've managed to make it efficient enough that we've been able to set it as the default. So all maps now look crisp and done with vector graphics. Well, in version 14.3, not only can we render maps in dark mode, we can also get actual nighttime satellite images. So for example, let's say we do the following. We can say a night image of the country of Sicily. There it is, with lights at night. Well, we've worked pretty hard to pick nice crisp colors for our default maps, but sometimes you actually want the base map to be quite bland, because what you want to really stand out is data you're plotting on the map. And that's what happens by default now in functions like GeoListPlot. If we plot capital cities in Europe, we'll find that the base map is very bland. But we can always tell it to go and actually show more detail, more terrain, or whatever, if we want to. Well, there are endless subtleties in map making, some of them mathematically quite complex. Something we finally solved in version 14.3 is doing true spheroidal geometry on vector geometric data for maps. And so the consequence of this is that we can now accurately render and clip even very stretched geographic features. Like, for example, let's take a look at this. Let's do a geoprojection of the world that's orthographic, centered on where I am. Even though Asia is very, very stretched in this rendering, Asia's somewhere over, where is Asia? Asia is over there. It's still accurately rendered in this projection. So another new geographic function in version 14.3 is georeposition, which takes a geographic object and transforms its coordinates to move it to a different place on the Earth, preserving its size. So, for example, we could say take Africa and reposition it next to South America, and yep, it more or less fits. That was at least with this particular rotation, you can see Africa sort of geometrically fits onto South America, kind of suggesting continental drift, although that was thought to be a crazy theory for a long time until it turned out to be true. Well, we can also determine things like noticing that if we put Greenland on top of Africa, let's say, it's actually pretty small, despite the fact that Greenland looks huge in Mercator projection maps. In the actuality of how large it is on the surface of the Earth, it's quite small. And there it is, placed in southern Africa. Well, needless to say, because we always like to make things as general as possible in Wolfram language, you can do georeposition off-planet as well. So this is taking the US and repositioning it on Mars, centered, having New York City centered at the position of Olympus Mons on Mars. So yeah, Mars is bigger than the US. Moon is about the same size. All right, let's continue. Well, so next topic I want to talk about is, I called it in the post I wrote, a better red, introducing new named colors. So here's the situation. You say, I want to show it in red. You might say, well, what exactly is red? Is it pure RGB color 100 or something slightly different? So 20 years ago, we introduced symbols like red to stand for pure colors like RGB color 100. But in making nice looking designed images, one usually doesn't want those kinds of pure colors. In fact, a zillion times I've found myself wanting to slightly tweak that red to make it look better. So in version 14.3, we're introducing the new concept of standard colors. So for example, standard red is a version of red that looks red, but it's sort of more elegant than ordinary red. So this is what it looks like here. If we, it may be a little bit more obvious if I switch to light mode there. There's the sort of the full blast of red, and then there's standard red, which is a slightly less pointy version of red. A zillion times in working on things I've written, I've got to tweak these colors to make them really be elegant looking colors. Still in text, if you described, oh, that's a red curve, it's fine to call this thing here red, even though it's not precisely RGB color 100. It just looks better. So sometimes the things are a bit further away. That's green. Let me make those a little bigger. That's green and standard green, and yellow and standard yellow. And standard yellow has the feature that if I go to dark mode, standard yellow still looks, well, it's going to look good in dark mode, but in light mode, standard yellow will look good, but yellow itself will tend to wash out in light mode. Well, these colors also look good. Not only do they look good as background colors, they also look good as foreground colors. And that is that. Let's just do this. So that was those same colors, standard red, standard green, standard yellow, as background colors. That's one of the reasons that the standard yellow is a little bit orangey rather than pure yellow, so that it can also work as a background color. And we can, oh, I should show you that in light mode, if I switch to light mode here, the text will turn black, and it still works on those background colors. The colors have been chosen so that they work with both light white text and black text. So these are also colors, the quote standard colors are also colors that have the same color weight, in the sense that, like our default plot colors, they're balanced in terms of emphasis. So that means if you plot 10 curves with in these standard colors, those 10 curves will all sort of look like they have the same level of emphasis. It's not like the red one will stand out relative to the other ones. So let's see, is this what I think it is? No, that's just showing that you can even in, that's just showing the white text. I could even have white text here in light mode, and it'll all work just fine. Okay. So we got a whole range of these standard colors that look pretty nice, I think. So, there'll be a standard, standard purple that looks a little different than ordinary purple, but they're all made to be aesthetic. And I suspect going forward, I'll normally be just using standard red and standard purple and so on, rather than the raw red. If I'm doing something like image processing, I might be using the raw red, but if I'm trying to do nice visualizations, I'll use standard red instead. Okay. So we've also added, so we've had for a long time, we've had colors that we call light, things like light purple. That's not some, we've also added in version 14.3 dark versions of all colors. We've tweaked some of the light colors a bit, actually, in this version. But now we've added, so you can have standard purple, light purple, dark purple. These are all designed colors, as opposed to sort of pure purple, which is just the RGB values, red and blue, that you would expect for purple. Sorry, this is a... So the whole story of dark mode and light-dark switching introduces, well, yet another issue in the specification of colors. So if you click a color swatch in a notebook, click that color swatch, you'll get an interactive color picker. In version 14.3, this color picker has been pretty much completely redesigned, both to handle light and dark modes and generally to streamline the picking of colors. Previously, you'd be, by default, picking colors with sliders. Now there's a much easier to use color wheel here, and with an opacity slider, that's the opacity slider there. If you want sliders, you can ask for sliders. There's the sliders controls. But by default, you get this kind of color picker wheel. You can also choose different color spaces. This is RGB color. We could choose hue, saturation, brightness, hue color. That will, if I say OK here, that will return a color. That's a color with opacity. But that color, if I look at the input form of that, it will be a hue with opacity in that case. Okay, well, so what about light-dark switching? Well, if I want to know what's this color going to be like in light versus dark. So in the corner of the color picker, you see this little, I don't know if you can see it, it's probably a little small on the screen. There's a little sun moon icon and a check mark next to it. So if you click that check mark, then the color you get will automatically switch in light and dark mode. So selecting, depending on different, let's see, if I switch this, oh, in light mode, what happened? There it is in dark mode. I think I switched, did I set that on? Okay, so here, oh, I see. Over here, I'm showing that's what that color would be. This check mark here is deciding whether I'm going to show the light-dark design interface or not. So this is now showing in light mode, this is now showing in dark mode, what that color would be in dark mode, and I can go ahead and set the color in dark mode separately in the color picker. So, and also, yeah, this is allowing me to set it in light mode, in RGB, and in dark mode, also in RGB, or I can just go to automatic here, and I can use our automatic algorithms for doing light dark switching. Yeah, so it's all very subtle. This user interface design is very subtle, and depending on whether you bring the color picker up in light mode or in dark mode, you'll get different defaults here, and it'll all just do the right thing. All right, more on the spiffing up of graphics. So version 14.2 had all sorts of great new features, but one sort of little enhancement that I see and appreciate every day is the spiffing up that we did of default colors, replacing our plot colors and so on. They automatically immediately give sort of graphics more zing, generally make them look spiffier. So in version 14.3, we've continued the process of spiffing up default colors, generated with all sorts of functions. Let me see if I can show you this. Let's look at something like this here, and let me go ahead and look at that in version 14.2, if I can do that. Here's the version 14.2 window. Now I'm going to look at this in version 14.2. Let's make that density plot over here in version 14.2. There it is. Okay, there are its colors. Let's go ahead and make that density plot now in version 14.3. And I think it's spiffier and zingier. Another example, that's very something I do a lot, is make cellular automaton pictures in version 14.2. This is using the colors option for color rules, which didn't exist in 14.2, so I can't use it there. That's the default set of colors, just black and white for that cellular automaton. If I put that over here, I'll get the same black and white. But now there's a new option for array plot for color rules. Normally you can specify explicit colors for different values here, but now you can also use the quotes color rules, which automatically colors these images. And it works for larger numbers of colors as well. So let's see, we can do that here. And of course, all these colors are set up so that if I switch to dark mode, they still look really nice. Okay, another thing we've improved in version 14.3 is the handling of meshes, so that they sort of gradually fade out when you get a finer and finer gradation of the mesh. So here I'm saying mesh to true, and in the first picture here, maybe if I switch to dark mode, it'll be more obvious. In the first picture here, you can see the mesh, I hope. By the time you get to the third picture, you can barely see the mesh. It's been faded out. Okay, in 3D here, we can in an array plot 3D, for example. Let's make an array plot 3D. Now we have in version 14.2, this was just grayscale. Now it's in a nice color. Well, there are all kinds of updates to colors for all sorts of things here. For example, let's look at doing automated theorem proving. So we can say, that was the 14.2 version. Well, I just closed my 14.2 notebook. Let's do the 14.3 version. This is just suffice it to say this looks a lot nicer than it did in 14.2. I'll show you it in 14.2. What the heck? Let's make a 14.2 here. This is the same thing in 14.2. We've just spiffed it up, made it look nicer colors, some nicer rendering. And this is a proof graph in 14.3. Okay, in addition to colors, another significant update in 14.3 has to do with labeling and plots. So let's make a plot. Let's make, for example, a picture of a feature space plot of flag images for countries. So it's going to grind away for a little while here, and eventually it should come back. I certainly hope it will eventually come back with okay, it's having to do a bunch of fancy machine learning to compare the images of all these flags, but hopefully it will have done that really soon now. Come on, wake up, what's going on? I guess it's doing, why is this taking so long? I don't know. Anyway, the thing I want to tell you about is the question of once this finally comes back, and I don't know why it's taking so very, very long. Very odd that it's taking so long. It's suspicious and strange. I'm just going to switch to light mode, not that I think that will make any difference. I don't know what it's doing. That's a very odd situation. Oh, there it is. Okay, it finally came through. I guess it had a lot of fancy machine. Oh, probably maybe it was downloading some machine learning neural networks. But anyway, so what we see here is a bunch of these sort of positions of different flags will be in, but we're only showing labeling for a few flags. There's a cluster from the Antipodes, I suppose, there that all look rather similar, and a cluster from Europe. Well, that's Mexico, but in over here. Now this is a do you know your flags story. That's not, no, what is that? I'm sorry, that's wrong. That's, let me not get all my flags wrong here. In any case, the question is what happens if you want to give denser labeling, okay? And so now what we've added in version 14.3 is the notion of a labeling target. So labeling target all, I don't know, oh gosh, I hope this doesn't take as long. Labeling target all will try and label every single flag here. So it might take it a while to do that, figure out where everything goes. But it's going to be very much a very much denser labeling of the plot. And so we can also do things like we can say here we can say okay, we can ask it to do dense labeling. Oh, there we go. There's our label where we said label, just put labels in for everything. Okay. We can also ask it to do dense labeling, or we can ask it to do, we can say something like labeling target arrow 0.2, which means label, attempt to get a labeling density of 0.2. Or we can do more elaborate kinds of things where we say, make it have a labeling target that allows the labels to only go in certain positions relative to the data. And I think I want to continue waiting because it's just running here. Yeah, wake up. Still generating this. Okay. Oh, come on. I want to continue waiting because I think this is going to produce a nice picture. One of the things we did in yeah, one of the things we want to do here is all right, I'm just going to abort this. Is to have the idea of plot interactivity. Oh, what's happening? Oh no. What did I do wrong? Did I say? Let me see. Let's just check things are basically alive here. That's a good sign. All right, let's try now doing this again. Something is very wrong. Let me just try doing something slightly different here. Hold on 1 second. Let's try this now. That looks better. Okay, so this is now making a 3D list plot. And by default, every one of these points has something interactive associated with it. We can make this, we can go around here. Sometimes, for example, if by default, there is a the interactivity, if you have a very big plot, interactivity and storing and sending over all of the data to make interactivity possible can be very big and very unwieldy. We have a bunch of heuristics for deciding when by default that interactive data should be sent over and so on. But in version 14.3, there's a new option, very relevant if you're doing things like just generating things for sort of printed output. What was I going to show you here? I think this was I was just going to show you the labeling target. Yeah, there's what happens if we go to labeling target 0.2 for the 3D graphic. So there we've tried to label lots of things. I wonder what happens if we say labeling target all. Just live dangerously. Let's see what it does. Okay, so there it will label every single point, as opposed to like labeling target 0.05, it'll label practically nothing. One thing we can do now is to use plot interactivity. So if I say histogram, random real, I don't know, 1,000 here or something, we'll get, oops, that's not, what did I just say? I should have said random real 10, 1,000. I'll get a histogram, and by default, I see all kinds of interactivity on these histogram bars. But if I want to switch that off, I can say plot interactivity to false, and now I will just get a raw histogram without any interactivity there. And that's a good thing if you have a very large image and you don't want to send over all the extra interactive data, or you're just trying to produce something for kind of printed output. Okay, let's move to in a different direction. I'm going to talk about something now that we've been intending to have ever since version 1.0. In version 1.0, we introduced the symbol star star to represent non-commutative multiplication. I already showed you something here. I typed in star star, but in all previous versions, it would have just written itself out as star star. But now star star turns into this object here that represents non-commutative multiplication. Star star has always been non-commutative multiply. If I ask what's the full form of this, will tell us it's non-commutative multiply. We've had non-commutative multiply in the system since version 1.0, but it hasn't really done much. In version 14.3, 37 years later, the future is finally here, so to speak, and you can actually do non-trivial computations with non-commutative multiply. It's a general non-commutative form of multiplication. So let's take a look at what kinds of things you can do. Well, you can do things like you can say non-commutative expand. And so here I've got some non-commutative multiplies in an expression. I'm going to do non-commutative expand, and I'll see that I get non-commutative multiplication out. This is not your average expansion as it would be with an ordinary polynomial. This is a non-commutative polynomial. There's another new thing we see here, which is x superscript 3 with a little tiny non-commutative multiply sign underneath it. That represents generalized power, a non-commutative expand generalized power. So the big deal here is that not only can we expand things out with non-commutative multiplication, we can also, algorithmic drum roll, simplify them. It's a different kind of algorithm than you need to simplify to factor things like polynomials, but it's something we can now do in version 14.3. So notice, by the way, there isn't a unique factored form for our non-commutative polynomials. And sometimes if you do something like this, where you expand something, then you simplify it again, you won't necessarily get back to what you started from. With the non-commutative polynomials, different mathematical behavior from an ordinary commutative polynomial. Well, okay. So this symbol here represents sort of general non-commutative multiplication with no particular properties. But there are many forms of non-commutative multiplication that are also useful, like a notable example is dot. So in version 14.2, we introduced array expand, sort of a special case of all of this, where we're just using dot as our multiplication operation. And we can do the same thing here using non-commutative expand, the new general non-commutative expand with, can we, what's happened differently there? With, oh, I see. This is just array expand, which just has x dot x dot x. This is the full non-commutative expand using dot as its multiplication operation and using this let's see, it's now using generalized power, and in the generalized power, the way we're representing it is the thing that it's powering is this little sort of blob underneath the exponent there. So in this case, it's a dot powered. In that case, it's a non-commutative multiply that's powered. Okay, so we can check that those two things are the same, that the result from non-commutative expand that's using generalized power and the result from array expand, we can check that they're the same just using full simplify. There it is. They're the same, but they're written out differently here. Okay, well, one of the things that we get from our new algorithms for non-commutative multiplication is we can do more powerful symbolic array operations. Like here's an example. This is saying A, B are both matrices, n by n matrices. This is now A inverse, blah, blah, blah. We can array simplify this, and we'll get that this result, that this is an n by n identity matrix. Well, how does this work inside? At least in multivariate situations, it's using the non-commutative version of Grosvenor bases. So Grosvenor bases are a core method in ordinary commutative polynomial computation. In version 14.3, we've generalized them to the non-commutative case. So you'll find non-commutative Grosvenor bases. This is something, again, it's a feature that people have been asking for probably nearly 30 years, is to be able to do these kinds of things. But this is an example of a non-commutative Grosvenor basis now working beautifully in version 14.3. Took a while to figure out how to do these and implement them, but it's done now. Well, let me not explain how Grosvenor bases work. This is kind of an example where you can sort of understand, sort of you're giving a set of expressions that are sort of assumed to be zero, and and this is now sort of giving simplified conditions for that. All right. Well, non-commutative algebras show up all over the place, not only in math, but also in physics, and particularly quantum physics. They can also be used to represent kind of a symbolic form of functional programming. So for example, here is this is using non-commutative collect, and it is using this is using a composition operation. This is the composition operator, and now we are doing non-commutative collect with respect to composition, and this is now showing us these compositions of functions can be collected together like this. And another thing that we've added in version 14.3 to support non-commutative everything is a commutator function. Commutator of x and y is the non-commutative multiplier of x times y minus y times x. Very common in quantum mechanics. These commutators are equal to a commutator of two conjugate variables like position, momentum tends to be IH bar and so on. But these are things that we can just define mathematically like this. Well, we can, if we pick something in physics, like a famous commutation relation is the commutator of two Pauli matrices. So this is Pauli matrix 1. If we just just explicitly evaluate these Pauli matrices, I can look at the commutator of those two Pauli matrices 1 and 2 with respect to dot is 2i times the third Pauli matrix. We also have anti-commutative function as well. So a function like non-commutative expand by default assumes that you're dealing with a non-commutative algebra in which addition is represented by plus and multiplication is represented by non-commutative plus, and that 0 is the identity for plus and 1 is the identity for non-commutative multiply. But if you give a second argument, you can tell non-commutative expand that you want a different non-commutative algebra. So let's say dot comma n represents non-commutative algebra of n by n matrices, where the multiplication operation is dot and the identity is oh dear. Is the identity matrix. No, this is a mess. The identity matrix of the n by n identity matrix, symbolic identity array of n. So let's see, if we have tensor product, let's see if we can do this. Let's define our own non-commutative algebra here, where we say explicitly, this is an algebra, and we say explicitly multiplication is m, addition is a, unity is o, 0 is z, and so on. We're giving commutative variables, scalar variables. That's sort of the full shebang of our own non-commutative algebra. And by the way, we can also define kind of tensor product. There's also a built-in version of tensor product algebra with a tensor product symbol. So let's just remind ourselves, tensor product, I'm afraid this is written wrong in the piece we just posted, but should get fixed. Tensor product is represented with a circle times circle times without kind of little whiskers sticking out. That's our ordinary tensor product, as opposed to a modern non-commutative multiply represented with star star that has it's kind of similar, but it has little whiskers sticking out, representing its sort of generalized nature relative to ordinary tensor products. Okay, but having defined this algebra by explicitly giving its multiplication operation, et cetera, et cetera, et cetera, we can now say do a non-commutative expand of this expression here. And this will happen where there's our multiplication operation. We can see the little generalized powers, m powers with little tiny m's sitting in there. I can make this a little bigger so we can see that. Okay, that's the world of non-commutative multiplication, non-commutative algebras, new in version 14.3. All right, let's go to a different area. quite different area. Let's talk about some geometry. Let's talk about the visual annotation of regions. So, for example, let's say we have let's say we've got some function. Let's say we've got a region, a torus. Now we want to plot a function over that region. So in 2D, we can use region plots and so on to do that. Here now we're using surface density plot 3D. That's a new function in version 14.3 to plot, in this case, norm of p minus the unit vector in the x direction on this particular surface. And so you can do this on any kind of surface. So let's plot the norm on a space shuttle. There we go. And there's a console plot version of this as well. So for example, we could take the surface contour plot and plot that over a, come on, wake up. We can plot that over a bunny. Wasn't so easy to do that computation, but now we plotted this norm of P as a color in this contour plot over the bunny. Okay, but let's say you don't want to plot a whole function over a surface, you just want to highlight some particular aspect of the surface. Well, you can use a new function in 14.3, highlight region. So here I'm saying highlight the region on a sphere that corresponds to those sphere points. And yes, highlight region is kind of clever. It makes sure that those points are visible and don't just get sort of sliced by the actual surface. Well, we could as well say we want to highlight just a region that's we're highlighting a ball on the sphere. There it is. It will work. This whole highlight region idea will work in any number of dimensions. So this is highlighting a region in 2D in a Menger sponge. Okay. So another useful feature about surfaces in version 14.3 is function interpolation now works on any kind of surface. So we can say interpolate the function sin x cos y over this region here. And we'll get an interpolating function that is an interpolation over that surface. And now we can use some, come on. For some reason, things are running really slowly here. I don't know why. Okay. We can use that interpolating function, sin x cos y, interpolated over the surface. We can now make a surface density plot 3D over that surface using that interpolating function. So there we have the result. Okay, let's talk some more about 3D geometry. Let's talk about curvature computation and the visualization of that. So let's say we have a 3D object. I have a simplified mesh of a cow. There it is. Now, let's say we want to compute. We can compute the Gaussian curvature of that surface. So we can compute the region Gaussian curvature of the cow for every point P on the cow. And now we want to make a surface contour plot 3D of that Gaussian curvature. So this should make a slightly difficult computation, but this is going to plot the Gaussian curvature essentially over the, there we go. So that plotted the Gaussian curvature of the cow over the cow. It's not that exciting. I guess it's a discrete pattern, so it has some, its curvature is just determined by these discrete dihedral angles and so on. Well, let's say we have a parametric object. Let's make this kind of region. That's a nice smooth object. Again, we can compute the Gaussian curvature here. And let's go ahead and do that and make a surface plot of the Gaussian curvature with the higher curvature at the corners there. Okay. So we can also, for Gaussian curvature, we can also get exact results. Well, we can get exact results for surfaces in general. We can say, what's the nearest point to 111 on that implicit surface? There's the result. Now we can say, compute the Gaussian curvature of that region, of that 3D object at that point. There we get an exact result. So there are other kinds of curvature. Gaussian curvature is some combination of, so this is the mean curvature computed for a particular surface. We can compute the max and min curvatures and so on. So for example, here we could say the max curvature of that region at the point we defined before, and we'll get a result here that's different from the Gaussian curvature. So, I mean, these surface curvatures are in effect the 3D generalizations of the arc curvature that we introduced actually more than a decade ago now in version 10.0. So the min and max curvatures correspond to the min and max curvatures of curves that are laid out on the surface, and the Gaussian curvature is then the product of these. Mean curvature is their mean. So you can see all these results there. All right, let's go on talking about geometry and surfaces. Let's talk about geodesics and path planning. So the question is, if you're on a surface, what's the shortest path from one point to another? So in version 14.3, you can find that out with find shortest curve. So this is saying on a sphere, what's the shortest curve joining the point 001 to the point 010? And there it is. You can see without its sphere, it's a little hard to see what's going on, but that's the curve in 3D space that is the shortest curve, the geodesic curve, joining those 2 points. Well, we can use the highlight region thing that I was just telling you about to show us both the sphere and that geodesic on the sphere. There it is. Well, it's more complicated. You can do much more complicated cases. Here's the highlighting a region, highlighting the shortest curve on a torus. And let's see if we can compute this. Solving a bunch of differential equations, grinding away, hopefully computing the shortest curve on a torus. There we go. There's the shortest curve between those 2 points, kind of wrapping in that somewhat complicated way around the torus. Fancy piece of differential geometry. Well, let's make it even a little bit more difficult. Let's say the object we're dealing with comes from some data, like here's Phobos, moon of Mars. And let's say, now we say, okay, let's pick 2 random points here. And I don't know whether I'll get interesting points, but we'll do it. We'll try it anyway. Those are 2 random points. On that random point on that surface, ds is that piece of geometry. So this is picking 2 random points on that surface. And now let's try saying highlight region of the shortest curve between those 2 points. Where are the points? Where are they? Oh, super boring. They were really close together. Well, let's we can also ask, what is the shortest curve distance between those points? And there it is. Or we could be a little bit more ambitious and we could say, let's find the shortest curve distance between 25 random pairs of points in on this object on Phobos. Where should we put the freeways on Phobos, so to speak? Here we go. So there are 25 randomly chosen shortest paths on that geometry. Okay, well, the region can be really complicated. So for example, let's say that our region is a Menger mesh. So let's show you the Menger mesh. There it is. So let's now try and find a shortest path through that. Isn't that cool that you can find a shortest path? I've made the thing low opacity so we can kind of see through it, but that's the shortest path kind of always being on the surface there. Well, we're looking in 3D so far. We can also do the same kind of thing in 2D. So for example, here is the shortest curves, several shortest curves through a mesh. Let's see if it can do this. There we go. There's the shortest paths through this mesh where the shortest paths are ending up at these different points here, and it's routing the path, sort of planning its path through this mesh with holes. Okay, what's it good for? Well, one thing is path planning. So we can go ahead and look at this region. So let's go ahead and we have here sort of a collection of furniture. But now if we want to know how will a robot of a certain size fit around this furniture, the first thing we do is a region dilation that effectively looks at how close can the robot ever get, what is the effective excluded region for each piece of furniture based on a robot of a certain size. Assume it's a circular vacuum cleaner or something. So if we invert this relative to this kind of gives us this area here, the blue area gives us the area that the robot can move in. These areas here are excluded. Well, now we can use find shortest curve to do path planning for the robot here, and it's going to highlight the regions that are the shortest curves in this space that go from this point here to points over here. And you can see that sometimes it goes around that sofa or whatever it is that way, and sometimes it goes around the sofa the other way. All right, a little bit more on geometry. Let's talk about geometry from subdivision. So creating realistic geometry is hard, particularly in 3D. So one way to make it easier is to construct what you want by combining basic shapes, say spheres and cylinders and so on. And we've supported that kind of constructed geometry since version 13.0. But now in 14.3, there's another powerful alternative, starting with a skeleton of what you want and then filling it in by taking the limit of an infinite number of subdivisions. So, for example, let's start with a very coarse approximation to a cow. And now let's say make a subdivision region by recursively filling in, by recursively sort of smoothing things out relative to that skeleton. And now we have kind of a smooth cow. Well, it's kind of pretty typical in these kinds of things to start from something kind of mathematical looking like a spiky, and then do these subdivisions, do the smoothing, and end up with something that looks a lot more sort of natural or biological. So for example, let's say we start from a cube, we can just do a successive subdivision of that, and eventually we'll end up from a cube with successive subdivisions, we'll eventually end up with a sphere. But let's try a more realistic example. Let's say we have the geometry, the approximate geometry of a bone, but we want to make a kind of more realistic kind of approximation to a bone. Well, we can use subdivision region and we'll get now this smoothed bone. Well, like other computational geometry and Wolfram language, subdivision region works not just in 3D, but also in 2D. So here is a Voronoi mesh in 2D. Those are the regions closer to each point here than they are to any other point. And we can take that Voronoi region, and let's say something we've been able to do for a couple of versions here is split this into mesh primitives. So we're now breaking that Voronoi mesh up into its individual little, paving stones or something that fit together. If we subdivide, if we apply subdivision region to each of those, we will get essentially sort of stones, rounded stone approximations to our puzzle pieces up here. So that's kind of a 2D application of subdivision region. Well, in 3D, we can just make something cool there. We could say take a 3D Voronoi mesh and do the subdivision on the 3D Voronoi mesh that we get. Might take a little while, it's a difficult computation. And there it is, 3D stones made from our subdividing our Voronoi mesh in 3D. Okay, let's talk some more about meshes. Well, one thing we introduced in version 13.1 is, let's say we have a region that's just a bunch of points. Well, in 13.1, we introduced the possibility of making a reconstruction mesh, making an approximation. Again, it's a difficult computation here, but making an approximation to this as a there we go. Okay, now we have an approximated dragon, where we got that by reconstructing the surface from the 3D point cloud. Well, the problem is that there's all kinds of crinkling in this dragon that comes from the fact that it was reconstructed from those discrete points. One thing that's pretty common is that we want to smooth that mesh. So let's take the dragon we got there and let's smooth it. And this will now make at least a slightly smoother dragon from that mesh, from that kind of reconstructed mesh. One issue here is that this has lots of polygons in it. And when we're doing operations on this, or we want to 3D print it, it's often important to simplify the mesh. So here we simplified that mesh, we got something a bit more faceted, but even though it's a bit more faceted, the advantage is that it has a vastly smaller number, 10 times fewer polygons in that 3D object than we had before. So another thing we've done in version 14.3 is the function remesh, which tries to take a mesh and make it a more reasonable mesh. So it removes very pointy polygons and so on. In general, it tries to remove polygons that would cause trouble if you were doing things like 3D printing or doing finite element analysis. We're working on a series of kind of increasingly sophisticated kind of mesh simplification functions. Those will be coming in future versions, but remesh is already a very good start to that. Okay, next topic, rendering molecules. So let's say we have a molecule like caffeine, and we want to make a molecule value plot with a new function, molecule value plot, which allows us to render a molecule with values of something indicated on that plot. So in this case, we took a raw picture of a caffeine molecule and we annotated it, coloring each atom, coloring it according to the oxidation state of that atom. So for example, we can do the same thing. This is now in 3D case, molecule value plot 3D, a caffeine molecule showing, well, there's showing oxidation states, but now we can do something like we could show the bond length, which is now a continuous variable, shown as and most bonds are a bit over an angstrom in size here. So this is showing the colors of coloring these bonds by those lengths. So another new function in chemistry in version 14.3 is molecule feature distance. So we can say what's the in molecule feature space, what's the distance between caffeine and theobromine as the result. And so, for example, you could use this notion of molecule feature distance to make a clustering tree. Here we can take a list of amino acids and we make a clustering tree showing the sort of relationships between those different amino acids. Well, when we first introduced molecule, we also introduced the function molecule modify. Over the years, we've been steadily adding more functionality to molecule modify. In 14.3, we added the ability to invert a molecular structure around an atom, in effect, flipping the local stereochemistry of the molecule. So let's take a look at that. So this is now looking at cephalexin inverted around a, that's doing the inversion around a particular atom. And now we can compare ordinary cephalexin with cephalexin that's had an inversion done around a particular atom. And we can see these things have different stereochemical structure. All right, talking about molecules. Famous kind of molecules for us, at least, are proteins. That's what we're mostly made of. One question is, given a protein, given an amino acid sequence here, this is a biomolecule representing an amino acid sequence, we are asking, one thing we can do is say, what is the three-dimensional structure of a biomolecule with that amino acid sequence, a sequence of amino acids? What is the 3D structure of that? Well, in previous versions, we have been able to call external services to fold molecules. Now in version 14.3, you can actually fold the molecule locally in your computer. Yes, it's a fairly large model. I think it's 11 gigabytes to download and then 30 gigabytes when you unpack it. But now I think the first one of these you do, it's going to have to load that model into its local memory and things. I should have been doing this when I was yakking about what it was doing, but it's going to load the model, and then it's going to be able to do this folding locally in your computer. So you're not limited, however many cores and so on you have on your computer, you can do this molecular folding locally. You can study lots of different molecules and so on. Let's hope that this actually comes through and does this. Let's keep it going here, but we're going to talk about, this will give our sort of machine learning estimate of the structure of the molecule. We can, when it finally comes through, it's, as I say, these networks are large, and this is loading it in on my particular computer. Something funny going on my computer. I don't quite know what's happening here. Maybe it's something to do with this live streaming, but seems to be running awfully slowly. Maybe we can check the let's see. There we go. Finally, as I start to talk about how slowly my computer is running, and I see it going back to, finally, it actually folded this molecule. And in this particular case, this has an experimental structure. I mean, I'm just going to let's we can, I just want to prove that this really did something here by changing, let's change that to a D, and let's try and refold it. And grind, grind, grind. Okay, it's folding, it's folding, it's folding. There we go. Now it changed it, didn't change it much. I guess that was just sitting somewhere in the alpha helix and didn't really do much. But okay, so in this particular case, that amino acid sequence is, I think, this biomolecule, and this should be the experimental version of that particular biomolecule. So they look pretty similar, but one thing we can now do is to say, let's take our version of the biomolecule with local folding, and let's align that to the experimentally determined biomolecule, and then let's plot those two things together, biomolecule plot 3D of those two things together with that caption. So what we see here is, yep, the experimental and the predicted and experimental versions. In this particular case, most of it follows quite closely between those two. So the folding was correct in this case. Well, we can compute other things. For example, we could compute the, we can biomolecule align lets one compute other things than this sort of combined biomolecule. That lets one compute the root mean square error, for example. 1.2 angstroms is the root mean square error, although there's clearly more error in some parts of this folding than others. Well, okay, version 14.3 introduces some other sort of versions of protein shape. So this is now for that particular protein. This shows Ramachandran angles. You kind of see the two different parts of the two different domains in that protein show up at different places in the Ramachandran plot here. We can also do a distance matrix between the residues, between the amino acids. That's another kind of signature of the shape of the protein. All right, that was a little bit on proteins and molecules. Let's turn to a different area. Let's talk about systems engineering. So for more than a decade now, we've had Wolfram System Modeler to let one build up and simulate models of real-world engineering and other systems. And by real world, I mean sort of an expanding range of actual cars, planes, power plants, and so on, with tens of thousands of components the companies have built, not to mention biomedical systems, things like this. So the typical workflow is to interactively construct systems in our system model product, then to use Wolfram language to do analysis, algorithmic design, and so on them. Well, in version 14.3, we've added a major new capability, also being able to validate systems in Wolfram language. Will that system stay within the limits that were specified for it? For safety, performance, and other reasons, that's often an important question to ask. And now it's one you can ask using system model validate. But how do you specify this? How do you specify the specifications? Well, that needs some new functions, like system model always, that lets you give a condition that you want the system always to satisfy, or system model eventually, that lets you give a condition that you want the system eventually to satisfy. Okay, so let's start with a toy example. Let's just look at this differential equation, very simple system here. And let's solve this differential equation and plot the result. There it is. Well, we can set this up as a system modeler style model. There's the equation. We're going to create an equation model. Now we're going to load up all this stuff. We're going to say simulation settings, stop time of 10. That's what we had here. Get these results. And this will now be a system model. We can, if we wanted to, we can take that system model, we can plot it as a function of x, so it'll actually simulate it as a system model and give out the same result as we got by just directly solving the differential equation in Wolfram language. But now we want to validate that system model. So we want to say, does the system model always, for all t, does it have the property that x of t is less than 1.1? Okay, so it's going to simulate it again, and it's going to say, no, didn't work, had a failure. Well, and if we look here, up here, there's 1.16, so it is indeed above 1.1. The system kind of whatever, it escaped somehow. Well, we can ask for this validation function, this system model validation data, we can ask lots of questions about it. Like we can say, where were the failure intervals? So there's the interval over which that model failed. We can make a failure plot, which is kind of a visual representation of where things failed. And we see there 0 to 10. And we see just this region here that is a failure region. Well, okay, what about a more realistic example? So here is this is a model, a very simple model of a car. This is not as beautiful in dark mode as I would hope it to be. It's strange that didn't convert quite to dark mode as I would have expected. In any case, all right, let's say we have a specification for this car that says apparently the US EPA has a highway fuel economy driving schedule. Following that, the temperature in a car battery, there's a battery here somewhere, can't be above 301 Kelvin for more than 10 minutes. So let's see, we want to translate that specification into something we can represent symbolically. And so what we want is can't be above 301 Kelvin, can only be above 301 Kelvin for at most 10 minutes. So we can use temporal logic to basically specify that. In version 14.3, we've introduced a bunch of temporal logic primitives for system models. One of those is system model sustain, and so this is the car model, and we say system model always that it does not sustain the temperature T being above 301 for between 10 minutes and infinity. So that's a kind of symbolic representation of the regulations that say you can't have that battery be above this. Okay, but now we want to know, well, where did it fail? So we can make a failure plot here of that. And there we have the result. And actually, if we simulate that underlying model that we had, here we're going to plot just the value of the temperature versus 301, we will see that indeed that's where it fails. It spends too much time here over the 301 Kelvin temperature point. So this is kind of the beginning of a lot of ability to sort of symbolically specify constraints on real-world systems. You'll see a bunch of things coming in future versions along these lines. This is the beginning of that. It's pretty neat that we can go from this realistic model of a car that has zillions of equations in it, and we can just give this symbolic specification and have it figure out, is that symbolic specification satisfied or not by this model in this way. And I should just emphasize, it's really very industrial scale. So, you can have a thing with 50,000 components in it, and what I just showed will work just fine. All right. So related to this, talk about control systems. So for 15 years, we've been building the ability to sort of design and analyze control systems. Complicated area. There are lots of different ways to look at a given control system, lots of different kinds of things you can do with a control system. It's also worth realizing control system design is a very iterative process in which you sort of repeatedly refine a design until all the design constraints you have are satisfied. So in 14.3, we've made it much easier to do this kind of iterative control system design by providing easy access to automated tools and also to multiple views of your system. So for example, here, let's look at a very simple system. Let's look at, this is an elastic pendulum. Oh, I can do an update. Shall I do an update? I'll update now. Reevaluate to use. That's a very nice mechanism, isn't it? Okay, so this is a control system representing our elastic pendulum. And for example, we can show the icon corresponding to this. There's sort of a picture of what our elastic pendulum should be looking like. And oh boy, well, I thought we'd solved the whole dark mode problem, but we didn't. Somebody didn't do what they should have done on these icons and convert them properly to dark mode. In any case, let's go back to dark mode because I like dark mode now. I'm getting addicted to dark mode. So let's see. One thing we can now do is sort of click this representation of the model in, I'm going to go to light mode because otherwise we're not going to be able to see what's going on here. So I can click this representation of the model. Now you get this kind of raft here of possible things. And I could, for example, say, let's see, I could say, show me this. This shows me, this is the display appearance of the model. Here I could say, show the model as this kind of block diagram, show the model in a different form, show it as this properties of the model, show the model as, what is this? This is show it as some kind of matrix form, show it, what's that doing? Oh, it's computing things here, okay. Well, these are just different ways to display this particular model, the thing that was by default displayed like this. So let's imagine that you have filled in numerical values for all the parameters in the model. So we don't have anything symbolic here. Now you can immediately do things like get simulation results from the model. So there we've got the that button should give us the simulation result from this model, which it couldn't do, although it should have said it couldn't do it in the symbolic case up here. Okay, I'm a little surprised it looked the way it did. Let's see. Oh, I see. We can get to a different, we might get to a singular value plot for that's the response of this particular system to, that's a sort of control theory type response curve for this particular system. You can take that there and you can click this result here, and then you can generate that directly as a singular value plot of that thing. That will now show you how to generate the singular value plot from this particular system. Well, there are lots of properties we could extract from this system. So, for example, we could extract the state equations from this system. So there are the equations that are corresponding to that system. And then if we wanted to, we could use ND-solve to solve these equations. But let's look at a slightly more sort of industrial example. So let's say we look at, what is this? It's not the same thing. Let's say we look at a model here. There's a more elaborate model of maybe these updates are the things that give us dark mode. Maybe that's my problem. I didn't update those. Anyway, there we go. This is a helicopter. This is a model for the pitch of a helicopter, more complicated control system. And now here we can get the state space model for that helicopter pitch model. There's a representation of the state space model for this. And here's a version of that model with numerical values filled in. And now we can ask sort of, how does this model behave? So to get a quick impression, we can use a new function, pole zero plot of the model. I think pole zero plot maybe also works just on functions, or if it doesn't, it should. But this is showing us the position of the poles in the complex plane and also the zeros in the complex plane. So in the world of control systems, it's a big deal whether the poles are in the right half plane, and which they are. So that means when there are poles in the right half plane, it means that the system is unstable. They'll be growing, exponentially growing. The perturbations will exponentially grow. That's what that means when those eigenvalues are in the right half plane. So now the question is, okay, what can we do to stabilize this system? Can we make a controller that we can put in this helicopter, which will stabilize it so it won't go unstable when the angles have the wrong values? Well, so we can make an LQ regulator as a controller, an LQ controller for this system. So we're taking our original state space model here. What is this? This is making a controller for this system. And now we can run this system with its controller in a closed loop. That's taking that original model, then running the controller in a closed loop. And now we can get the pole zero plot for this. And I'm actually a little bit confused by what happened here, because I would have expected, oh, I see. This is showing, that's right. So this is the original, that's right. The blue is the original model over here. That's what we asked to do, the model and the closed loop system with the LQ regulator, with the LQ controller here. So that's the original model, which goes to the right in the upper, in the half plane, the right half plane. And this is now the controlled model, which now only has poles in the left half plane. So we succeeded in making our system stable. So we can now ask, what does the system actually do? And so for that, we can ask for the input-output response of this closed system, and that'll give us those results. And if we plot that, this will show us that given these, so these are responses, this is showing that indeed the perturbations get damped out in this controlled, with the LQ controller, controlled closed loop system. This may all seem a bit abstruse. It's what control engineers have been doing for decades. At least, well, we have a fancy version of it here, but the general ideas of control theory have been around for decades. Actually, there's a new game in town that's also closely related to that, and that's reinforcement learning. Reinforcement learning uses the exact same methods, basically, as control systems. And so one thing you'll see coming in future versions is a merger of our control systems functionality and our machine learning functionality. And that's something that you can already do with some of these capabilities here, is use control theory on machine learning. We're also hoping to generalize it to other kinds of mechanism design and so on, and add greater interoperability with the rest of the system. All right, different area. Let's talk about graphs. Here's a binary tree with 31 nodes, and it spreads out pretty quickly. But if you have a tree, for example, let's say I have 2 to the 12 nodes, it'll try to spread that out in 2D, but it isn't a very nice regular layout of the tree. Well, in version 14.3, we have a new concept of hyperbolic radial embedding, which now lays this out in the hyperbolic plane. Poincare model, I guess, of the hyperbolic plane. So this is convenient if you have things that branch a lot, trees and so on. We are now able to do things with hyperbolic embeddings. We can actually use a hyperbolic spring embedding. So we are operating in the hyperbolic plane, but using that metric, but using a spring embedding. And I think that takes a little while. But we can have it. I'm surprised it takes it this long. Oh, there we go. So now, for example, we could pick a particular root vertex here to do that hyperbolic layout, and we'll get interesting pictures like this that do better in sort of hyperbolically laying out these graphs that branch a lot. Okay. Well, we wouldn't. You might have thought that by now, after all these years, we would have finished everything in calculus. And we're really close. We've done so many things. For example, in integral transforms, we've got Laplace transforms, Fourier transforms, Mellin transforms, Hankel transforms, radon transforms. Well, now we've added the last of the common integral transforms and the most difficult, the Hilbert transform. So Hilbert transforms actually show up a lot when one's doing things with signals. With the right setup, Hilbert transforms basically take the real part of a signal, say as a function of frequency, and if one's dealing with a nice analytic function, give its imaginary part. It's something that shows up a lot in scattering theory and things like particle physics and so on, quantum mechanics in general. Okay, Hilbert transforms. So let's do this Hilbert transform. Here we go, there's the result. And if we plot these two things together, we'll see a very characteristic resonance curve here with the corresponding phase shift effectively being shown there. So there's a classic thing if you're into particle physics. There's a classic thing for cross section versus phase shift, but it also shows up in lots and lots of other places. Well, needless to say, we can do fancy Hilbert transforms as well. Here's a Hilbert transform involving a Hermite function. Let's see what that does. Okay, there we go. It comes out in terms of a Dawson F function, fairly exotic. But we added the Dawson F function in version 7, so there it is ready to be used when we finally have Hilbert transforms of Hermite functions. Okay, talking of special functions. Like so many versions, 14.3 adds yet more special functions. So, and yes, after 4 decades, we're definitely running out of special functions to add, at least for univariate special functions. But in 14.3, we've got just one more set, the Lommel functions. And Lommel functions are solutions to an inhomogeneous Bessel equation. There's the equation, and there is a Lommel function showing up. They come in 4 varieties, and here's an example of plotting one of the Lommel functions, Lommel S2, in a particular region. There it is. In real imaginary parts. And what makes it difficult to implement all these special functions is we really do it properly. These special functions can be evaluated to any precision anywhere in the complex plane. They show up in solutions to differential equations and integrals, all kinds of things, in all kinds of different places. So here is the T2 Lommel function in the complex plane, there's all sorts of relations between Lommel functions and other special functions. Like here's function expanding the Lommel T1 for particular values in terms of Struve functions. And like other special functions, we can compute things like the function singularities of the Lommel functions. And we can even do integrals with Lommel functions. Let's see if we can do this. There we go. There's an integral of that Lommel function. So another set of special functions added for 14.3. Okay, another area that has been kind of filling in something that sort of a jump from version 1 is in matrices. So we've had matrices and many things that one can do with matrices since version 1. In version 1, we had null space, for example, for matrices. In 14.3, we're adding the function range space, which is sort of a complementary representation of subspaces. Null space is the null space, the kernel of a matrix. Range space, the complement of that. So there it is. Okay, another thing, projecting a vector onto the subspace. So in 14.3, we extended projection to allow you to project not just onto a vector, but onto a subspace. So here's the projection of the vector 110 into that subspace. There's the result. Well, these functions work not only numerically, but also symbolically. There's the result. The methods are rather different, but the results can be gotten in symbolic form. A somewhat meatier set of new capabilities have to do with decompositions for matrices. So we already had a bunch of matrix decompositions in version 1. Over the years, we've added a bunch more. In version 14.3, we're adding 4 new matrix decompositions. So the first one is eigenvalue decomposition. That is a sort of repackaging of matrix eigenvalues and eigenvectors to define a similarity transform that diagonalizes a matrix. So another new matrix decomposition is Frobenius decomposition, which essentially achieves the same objective as eigenvalue decomposition, but in a more robust way that, for example, doesn't get derailed by degeneracies between eigenvalues and so on, and also avoids getting complicated algebraic numbers from integer matrices like we already were starting to see here. Okay, so we're also adding a couple of simple matrix generators that are convenient for use with functions like Frobenius decomposition. So here's a companion matrix of the vector 1, 2, 3, and here's the Jordan matrix of lambda and 3. Another thing is sort of mixing matrices and univariate polynomials. So for millions of years, so to speak, we've had characteristic polynomial. Now we're adding matrix minimal polynomial, which is the minimal polynomial that sort of a polynomial special case. Let's see, it's the minimal polynomial. What does it give? That for which that I see that the matrix satisfies according to the Cayley-Hamilton theorem, I think. Talking of the Cayley-Hamilton theorem, well, actually, let's see. We can look at the Cayley-Hamilton theorem in action here by doing matrix polynomial value. So there's a generalization of matrix function. This is matrix polynomial value. This is the value of this matrix function. The value of this polynomial where we're going to be filling in a matrix in that position. And so here, following the sort of Cayley-Hamilton story, we indeed get 0 here. Okay, so it's actually sort of interesting what the relationship of this is to non-commutative multiply, and I'm sure I could work out how that all fits together. Okay, version 6, we introduced Hermite decomposition for integer matrices. Version 14.3, we're adding a version for polynomial matrices that uses polynomial GCD instead of GCD in its elimination process. So let's take a look at that. So this is polynomial Hermite decomposition and gives that result. We've got, going along with that, polynomial Hermite reduce for doing this with polynomial matrices. Also new in 14.3, a little bit of additional notation. We've got a new standard form notation for norm, and we'd actually use this in we'd use this in traditional form before, but now we're introducing that as a standard form version of representation for norm. Let's see, you can get this by typing escape norm, escape, and you get that kind of template that you can then fill in M for and so on. So a few other notations we've added: Frobenius norms, adjugates, pseudo-inverses, there they are. That's small but useful. All right, talking of small but useful, we are on to another thing. This is a long requested feature, with nested withs. So this is something I find myself doing a lot. You say f of x and y, and I say with y equals x plus 1, but now I will have to have an outer with for that x equals 1. Well, now finally, in version 14.3, there is a multi-argument form of with, where you can say with x equals 1, then you're sort of cascading withs. Y equals x plus 1, f of x, y. That all just works. Well, that's what happens if we do that sort of cascading with. But if we just put these withs in, if we put those two things in at the same time, then we don't cascade them. We don't set x equals 1 in the y equals x plus 1. And so we get out as a result f of 1 and 1 plus x. So how could we have told the difference between typing in this sequential width and this parallel width? Well, if you look carefully, the x here is green and the x here is blue. And that's the clue that we're going to do something different here. We have scoped the x's in here. We are successfully scoping the x in there. Now, by the way, that was doing that kind of syntax coloring was one of the very tricky issues in implementing multi-argument width. So as you add arguments, variables will sort of turn the right color to indicate how they're scoped. So for example, if I do something like this, x equals 1, x equals x plus 1, it sort of reddens up in this case to indicate that that's not likely to be it's not scoping the way you think it's scoping. All right, so that was multi-argument width. Another little convenience that I think I'm going to find myself using all the time is cyclic lists. So question is, what's the fifth element of a 3-element list? Well, I might just say it's an error, but an alternative is to treat the list as cyclic. And that's what the new function cyclic does in version 14.3. So cyclic of the list ABC of 5 gives B. And in general, if we just had said cyclic ABC of 1, we would have got just the first element there. But the whole point is that it wraps around and gives elements that would be gotten by doing sort of modular arithmetic and just wrapping around this list. So you can pick out any cyclic element, like the minus 100,000th element of this list. It says is B. Well, cyclic effectively provides a way to do computations with effectively infinite repeating lists. It's also useful, so it's useful for that purpose. It's also useful in less immediately computational settings. Like I wonder whether cyclic, I'm now wondering, now I'm just playing here, but I just wonder whether this works. Cyclic 1, 2, comma 50. Oh dear. Well, so much that's a design that should just work. Okay, meanwhile, not in the sort of computational area, but in just sort of using lists to represent things, here's something we might want. We have a matrix and we just want to fill in the background for the successive columns in the matrix cyclically as red, green, blue. That's how you can do it now. You just specify that cyclic wrapper to those colors and they will be filled in cyclically in this background. Okay, well, a very big thing in version 14.2 was sort of game-changer capabilities for handling gigabyte-sized tabular data, centering around our new function tabular. 14.3, we're rounding out the capabilities of tabular in several areas. First has to do with where you can import tabular data from. So in addition to local files and URLs, version 14.2 supported Amazon S3 and Azure Blob Storage, Dropbox IPFS. Version 14.3, we're adding OneDrive and Kaggle. We're also adding the capability to gulp in data from relational databases. So already in version 14.2, we allowed sort of the powerful possibility of handling data out of core in relational databases through Tabular. Now in version 14.3, we're adding the capability to directly import for in-core processing the results of queries from such relational databases as SQLite, Postgres, MySQL, SQL Server, Oracle. All this works through data connection object, which provides a symbolic representation of an active data connection and which handles issues like authentication. So let's try one of these. Let's say we've got a data connection object that represents this SQLite database. And now we can just take that whole thing and gulp it in. We just say import that data connection object, and we'll gulp in this whole database. as an in-core tabular. So one particularly frequent source of large amounts of tabular data is log files. In version 14.3, we're adding some highly efficient importing of Apache log files to tabular objects, also adding import capabilities for common log and extended log files, as well as import and export for JSON JSON lines files. So what's a good example of this? We can say, let's import this from Hugging Face. This is a JSON lines file, JSON-L file, and there's the result, came in nice and easily. So we're adding support for import as tabular from a whole bunch of formats. We're also adding in tabular, if you're dealing with geodata, we're adding geoposition as a column type in tabular, relevant if you're dealing with large-scale GIS data. Let's see. Well, as well as getting things into tabular, we're adding some new capabilities for manipulating data within tabulars and for combining data from multiple tabular objects. So new function in that area is column-wise combine. So a basic idea of column-wise combine is take multiple tabular objects, look at all possible combinations of rows in these objects, then to create a new single tabular object that contains those combined rows, well, that contains whichever of those combined rows satisfy some specified condition. Okay, so let's look at 3 tabular objects. Here we go. Let's set up these 3 tabular objects. So now let's set up a column-wise combined version of these 3 tabular objects where the criterion for including a combined row is that the values in columns A and B agree between the different instances of that row that are being combined. So there's the result for that. Well, there are lots of subtle issues that can come up here. We're doing an outer combination here, which we're effectively assuming that an element that's missing from a row matches our criterion. If it's missing, it matches. And then we're including rows with those explicit missing elements added. Okay, so that was the, let's see, this is the outer version of that with this. Is that what I want? No, it's not what I want. Oops, we're missing something here. Oh, well. Okay, so this is the outer version here. That will, so the previous version was just putting in rows whenever A and B, whenever the entries in A and B agreed between those rows. But now, I'm actually confused here what this is doing. This always takes a little while to understand what's happening. But we're basically having a different criterion. In this case, where, oh, I see, this was supposed to, oh, I see, this is combined. This was supposed to, these are cases, if I look up here, these are cases where the things did agree in A and B, but they didn't. Yeah, we didn't have a value for D and E, but in this case, so we just filled in missing in that case. But here we just removed those rows that wouldn't be able to be completely filled out. Okay, so there are all kinds of subtleties in this. There's another one. If in different tabular objects there are columns that have the same name, how does one distinguish elements from those different tabular objects? So, well, this is what happens. We're effectively giving these tabulars names, alpha, beta, gamma, in this case, and then we're doing the combination. So what it's doing here is it's making extended keys for these alphas, betas, and gammas. So it's like the alpha version of A, the beta version of A, and so on. Well, column-wise combine is effectively an n-ary generalization of join across, and join across represents the join operation of relational algebra. So version 14.3, we've also upgraded join across to handle more features of tabular, for example, being able to specify extended keys. And in both column-wise combine and join across, we've set things up so you can use an arbitrary function to determine whether rows should be combined. Rather than just do these elements agree, it's an arbitrary function that can be used. Well, okay, we might ask, why would one ever care about functions like column-wise combine and join across? A typical reason is that one has different tabular objects that give intersecting sets of data that one wants to knit together for easier processing. So let's say we have one tabular that contains properties of isotopes and another, so here's one that contains properties of isotopes and another that contains properties of elements. And now we want to make a combined table of isotopes, but now including extra columns brought in from the table of elements. So we can make a combined tabular using join across. And so this is saying that we want them to be combined when they start with the same, when the thing in the isotopes tabula starts with the word that appears as a name in the elements tabula. So there's the result. And so by default, we only get one column in the result with any given name. And so we're just seeing all these uraniums are here, but they're getting the atomic number from the elements tabula over here. We've knitted together these tabulars by doing this join across. If we want to disambiguate the columns by their source, we can do that by specifying a key in the join across. So we say these are things coming from isotopes, those coming from elements. Now we've got the whole shebang here where we've got the atomic mass from isotopes and the atomic mass from elements. For elements, it's averaging over the isotopes. With isotopes, it's giving the specific atomic mass for that particular isotope. So that's a story of enhancements to Tabular in this version. Another thing we've done with Tabular is to add a whole bunch of options for styling Tabular. So simple things, you can use image size to programmatically control the initial displayed size of a Tabular. You can always change the size interactively by just picking up that thumb and changing it. Isn't that cool? I want to change back to dark mode here. Let me change to dark mode just for fun. Lovely. Okay. We can also say what visual elements we should include. So for example, well, here, let's here actually, this is just changing this is changing the image size. Okay, great. Now let's decide which appearance elements. So let's say we want to include column headers. There we go. And we've, that includes column headers. I guess that's the, that's the default. So I don't know quite what, now let's see, appearance elements to none. What would happen here? Okay, no column headers. Oh, I see. There we have column headers, but no row labels here. So when we ask for column headers, now we have nothing. Okay. So now you can specify things like backgrounds, and now we can use the nifty new cyclic option, cyclic wrapper, to say take that tabular and show this with light green backgrounds. That's kind of unfortunate. I'm surprised that didn't, I guess we just told it to make a light green background. We should have done a light green a light dark switched version of that light green. I wonder what will happen now if we go back to light mode. Okay, now that light green makes sense in light mode. I wonder what would happen if we said standard green there. Okay, that looks a bit loud, but it will certainly work now also in dark mode. Okay, so there are many, 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 many corner cases. So for example, let's say we make a tabular and we make cyclic colors in rows and cyclic colors in columns. Columns, what happens when they overlap? Well, we have to do color mixing in those cases. It's all tricky stuff. And we can, for example, we could say, let's highlight a single color by giving a background where the column rules say the year column gets light yellow. So there it is, highlighting that particular column. We can also specify an item style where we say, make things in the year column bold and standard red. So there they are. Okay, so let's say now we can do things, more elaborate things. This is very convenient. In a tabular, we can say, I want to make color things to highlight, for example, every entry where the highway column is less than 30. HWY column is less than 30. And now we're highlighting rows that have that property. So we can very flexibly use arbitrary functions here to determine what rows get highlighted, what rows get what backgrounds in this tabular. So now this was just absolutely saying every time HWY was less than 30, make it light orange, but this is slightly more elaborate. This says rescale this value to be a blend from blue to red, rescaling that value by the column-wise value of the min-max of that. So what this is doing is it's saying column-wise value is saying compute this min-max, compute the min-max of all these values column-wise, and then rescale that with those column-wise values, with those column-wise normalized values, and then color the thing based on a blend of blue to red. So there we've now got this blue to red blend of these rows based on the rescaled value of HWY. And by the way, the last row, the rows here have no color because the HWY column happens to be missing in those cases, as we can see here. Well, similarly, same kind of idea as what I was just doing. Let's say I want to highlight all the missing values in yellow. I can just use an item value function and just say, if missing Q, make it yellow. Okay, so that's more on tabular and the formatting of tabular. All right, next I want to talk about semantic ranking. So say, which of those choices do you mean? You're shown a restaurant menu and you say to the person taking your order, I want the beef. Well, it probably didn't say just beef on the menu. It said probably fillet of this, of whatever, with whatever on it, and et cetera, et cetera, et cetera. But you just said, I want beef. How do we deal with that? Well, here's a menu, and we want to set up a semantic ranking of this. There's some items in our menu, and now we want to say, I just want dessert. Okay, so I probably don't want saffron-infused risotto, nor herb-crusted lamb chops for dessert. But if I say I want this for dessert, what this will do now is it will rank these, ranking them semantically, with the first one being the most desserty of them, in this case, chocolate mousse. So you can get all kinds of details here. You can use semantic ranking to get, for example, relevance scores. So we'll see here the most relevant is the velvety chocolate mousse. So semantic ranking is useful for using essentially natural language methods to pick between some large menu of possibilities. In version 14.1, we introduced semantic search, which actually uses semantic ranking as the final ranking for the results that it gives. But semantic search potentially searches a large amount of material, returning the most relevant items. Semantic ranking, on the other hand, takes a small menu of possibilities and gives you a ranking of all of those based on the relevance of what you specify. So semantic ranking, in effect, exposes one of the elements of the semantic search pipeline. And in version 14.3, we're also exposing another element, an enhanced version of feature extract for text that's pre-trained and does not require its own examples. So let me give you an example here. You can say, you won the lottery. I want a sentence vector for that. It's a big mess of numbers. In previous versions, feature extract insisted on trying to learn from examples that you gave it what kind of feature vector you wanted. Now, this is just taking a default feature vector for sentences, and you get that result. So by the way, the new feature extractors that we have also improve things like classify and predict and so on when operating on text. Okay, another topic. We're getting close to the end here, but we're not quite there yet. We've still got some other exciting things to talk about. Compiled functions that can pause and resume. So typically in Wolfram language, the flow of a computation is a sequence of function calls with each function running and returning its result before another function is run. But in version 14.3, we introduce, in the context of the Wolfram language compiler, the possibility for a different kind of flow in which functions can be paused at any point, then resumed later. So in effect, what we've done is to implement a form of coroutines that allows us to do incremental computation, and for example, to support generators that can yield a sequence of results, always maintaining the state needed to produce more. So the basic idea is to set up an incremental function object that can be compiled. The incremental function object uses incremental yield to return incremental results and can contain incremental receive functions that allow it to receive more input while it's running. So let's start off with a simple example. So this is an incremental function. We're kind of, let me just create this incremental function here, where that keeps, okay, it's going to run the compiler to generate a compiled incremental function as a data structure. And what it's doing is it's just, it keeps on computing successive powers of 2. And every time we call if, every time we ask for the next of this incremental data structure, we get that result. If I say next again, I'll get 4, and so on. If I just make a table of all the nexts, I'll get the following powers of 2. But so notice this if thing behind the scenes, its state is changing. Every time I ask for the next element of that sort of faux data structure, that dynamic data structure, it's running this incremental function to get the next element of that data structure. So it's as if the next data structure, it's actually an infinite data structure. If I keep on asking for next, if I keep asking for next, I'll keep getting the next element of the data structure. But it isn't already there. It's being computed incrementally by this incremental function. So in effect, every time this incremental function is running, it's yielding this result here, and then leaving that incremental function to go on being incrementally applied. Okay, let's look at a slightly more sophisticated example. Let's look at an incremental version of the Fibonacci function. So let's see here. This will give us Fibonacci, start with 0 and 1. Why aren't we starting with 1, 1? Seems wrong. I'm going to change it. Am I right? Is that right? That just seems wrong. I think it's wrong. Okay, let's do this. Oh, I see. That's silly. Okay, in any case. Okay, so then we say next, we get the first element in this Fibonacci sequence. If we now go and say make a table, then we see more elements in the Fibonacci sequence, where FF is always storing the state, in this case, these two values that store kind of the state of this Fibonacci generator. So let's see. So incremental function is an interesting way to organize code. You kind of get to repeatedly run a piece of code and get results from it, but with the compiler automatically maintaining state. So you don't ever have to explicitly take care of that or include code to do it. So a common case of this is in enumeration. Let's say you have an algorithm for enumerating certain kinds of objects. The algorithm builds up an internal state that lets it keep generating new objects. Well, with incremental function, you can run the algorithm until it generates an object, then stop the algorithm, but automatically maintain the state so that it can resume again enumerating objects. So here's an incremental function for generating all possible pairs. Oh, come now, where is this? All possible pairs from a specified list. So here we can generate all possible pairs from a list of 1,000,000 elements. So that will be 10 to the 12 pairs, which clearly won't fit in computer memory. So we couldn't actually generate all these pairs. But if we just say next, we can see the first pair that's in that dynamically generated incremental function data structure. Or we can go through and we can ask for the next 10 elements there, and there we'll see them. If we can, we could ask for the, we could do that 1,000,000 times, and then let's see what happens if we do this. Nest pf, no, actually we just need to say do pf next 1,000,000 times. And then we can say, it was nice and fast, isn't that lovely? And then if we say pf next, I predict that there'll be elements that start with 2s. There we go. So we went through the first, all of the ones, all the 1,000,000 ones, and then we got to the 2s and so on. Happened blindingly fast. We're maintaining the state of this generator as in this incremental function. So you can also use incremental function to incrementally consume some external stream of data, for example, from a file or an API. And we're going to use incremental function. It's sort of a building block for many kinds of data structures in the future where you can't see them all. You can only get pieces of them incrementally. All right, let's talk about another thing: faster and smoother encapsulated external computation. So we work really hard for decades to make things as smooth as possible when you're just working within Wolfram language. But what if you want to call external code? Well, it's a jungle out there with all kinds of issues of compatibility and dependencies and so on. And for years, we've been steadily working to provide the best interface we can within Wolfram language to external code. In fact, what we've managed to provide now is often a much smoother experience than the native tools normally used with that external code. So version 14.3 includes several advances in dealing with external code. First, for Python, we've dramatically sped up provisioning of Python runtimes. Even the first time you use Python ever, it'll now take just a few seconds to provision itself. So in version 14.2, we introduced a very streamlined way to specify dependencies. In version 14.3, we've made provisioning of runtimes with particular dependencies really fast. So let's try this on my machine here. Let's say we have dependencies where we're importing NumPy, full of all its copies of Wolfram language functionality, usually worse. But if you want it, if you have code that's written with it, I guess you should use it. If you're writing code from scratch, I wouldn't use it. Now this has set up a Python runtime with those dependencies on my machine, and you can run with it. It took only 0.7 seconds to do that. You can run with it without any further provisioning. So another thing we've done is to do things with R. We can specify external evaluation with R. This is something, this is just crazy language design on the part of R, but we're not going to go there. The fact that I don't even want to go there and what they did in this language design. Not the issue. Okay, we can also type this, and we will get. We have all these choices of languages that we can use in external evaluation cells. One of those is R, so we can type this thoroughly horrifying thing in here to get that computation done in R, okay, and get the result back. So one of the big technical challenges is in a piece of less than wonderful software engineering for R, can you actually set up R on to run with different dependencies within a single session? R is fundamentally not set up to do that. It's not set up to have these different instances running with different dependencies, but it's something you need to do if you're separately using different R functions or libraries within different functions in a Wolfram language session. So now we can do that, it's really complicated to do it. And maybe there are cases that are so pathological where the world of R is just too tangled to ever make it possible. But at least such cases should be very rare, and you should usually be able to use different R dependency collections on different functions. In R, we've also set up support for external functions, so you can have essentially pure functions with R as the external language. All right, next, back in our own pure ecosystem, turning notebooks into presentations. There's been an issue so we've had this idea. Notebooks are usually scrolling documents. You can scroll through them, but particularly if you're making a presentation, you sometimes want them to be more in kind of a slideshow form, sort of PowerPoint style. So we had various approaches before, but in version 11.3, that's 7 years ago, we introduced presenter tools as a streamlined way to make notebooks to use for presentations. So the principle of it is very convenient. You can either start from scratch or you can convert an existing notebook. But what you get in the end is a slideshow-like presentation that you can, for example, step through with a presentation clicker. Of course, because it's a notebook, you get all sorts of additional conveniences and features, like you can have a manipulate on your slide, or cell groups you can open and close. You can also edit the slide, do evaluations, and so on. It all works very nicely. But there's always been, just to give you a sense of how that works, I can go here and I can just say, new presenter notebook, and I'm starting to get, I don't know, let's start with one of these, create it. This is now a new presenter notebook with the various styles that are set up here. Okay. Well, there's been one big issue. You're fundamentally trying to make what amount to slides that will be shown full screen, projected, and so on. But what aspect ratio will those slides have? And how does this relate to the content you have? For things like text, one can always reflow to fit into a particular aspect ratio. But it's much trickier for graphics and images because these already have their own aspect ratios. And particularly if they're somewhat exotic, say tall and narrow, one could end up with slides that required scrolling or otherwise weren't convenient or didn't look good. Now in version 14.3, we have a smooth solution for all this that I know I, for example, am going to find really useful. So let's say we go. Let's just start a let's insert a new slide here, and now let's say in the toolbar here there is a template for a. If I can only find it. There we go. This is a template for that inserts a template for a full-size slide. So let's use that here. Paste an image there. Let me pick up an image. Hold on one second here. Hold on. I think I had some good images to use here. Hold on one second. There's some good images to use. Let's paste this image in there. Okay, so this is now my slide with that very long, thin image in it. Let me do another one here. Let's do this, and let's now do that. What did I just do? Oh, I didn't paste it into that. I pasted it not into my full slide image icon. I don't know quite why this has a cursor in it. It didn't have a cursor in it. And I don't know why this isn't resizable. That's also very odd. In any case, this makes things that actually it should just work with dragging. So let's just try that. I have this here. I just drag my image. Oh, I see. I can drag my image. Oops. I had. There we go. Now I can drag my image and it should just go in there. Okay. The point here is that if I say start presentation here, I will get a very red hello there. And now what I'll see, I'd set this up and I had set up I hadn't set up a separate slide for this. So let me go back and get out of presenter mode. Remember how to do that. Let's see. Oh, there we go. Okay. Let's see. So what I was doing there was I was making. Oh, yeah. What I did here was, yes. Okay. This is a fit to window versus fill window. Okay. So let's say fit to window there. Let's say. We'll say fit to window there, and let's say fill window down here. And these really should be separate slides. So I have to insert a slide break between these. And this is, you can see I haven't been using this enough, partly because it hasn't had the features I wanted. So now what should happen is that when I start this presentation, I've got my big red thing. I'm going to go forwards. Now this is full screen. It knew to make that as wide as the screen, but now this next one, it knows to not make that a thing that has to scroll. That's just the height of the screen. It's been scaled to be the height of the screen. This one here now is supposed to fill the window. So when it fills the window, it's filling it on all sides and it's too big on the left, so it just goes out of the window on the left, and it's just filling it's filling that. And the let's see. I think there's a command key for ending the presentation. I don't know why it isn't in that pull down in that menu there. It should be. Nothing is ever perfect here. Well, in any case, the main point is that we're able to make sort of images of any shape work in our sort of notebook authored presentations. This has been kind of a long time issue, and now it's fixed. Well, let's talk about some more user interface polishing. So it's 38 years since we invented notebooks, but every version we're continuing to polish and enhance how they work. So here's an example. Nearly 30 years ago, we introduced the idea that if you type dash greater than, you get a nice arrow. 4 years ago, version 12.3, we made it so that when you backspace through the arrow, let me make this bigger so you can see it more easily. When you backspace through the arrow, it breaks itself up again into those dash and greater than signs. Let's see. If you arrow backwards through this, it used to arrow through, in version 14.2, arrowing back through the arrow, so to speak, broke it into its individual characters. But now the kind of ligature that we created with the actual arrow, the cursor jumps back across the whole arrow. I mean, what we learned from experience is it's sort of strange and jarring to have something that looks like a single character, but when you arrow through it, it doesn't arrow in one gulp, so to speak. So it's subtle, but I think it's going to make it, it's going to be a thing that just makes it all that much smoother to kind of edit things in Wolfram language. So here's another thing added in 14.3. Let's say you have something like this. Well, but you really want to make it a list. Well, here's something you can do. You can select the whole thing and then just press Shift Brace and it will wrap that list. So and the same thing happens with brackets and parentheses. So in other words, you've got some object, you select the whole thing, and you can just press a single key to wrap it. Now, if you keep pressing a key, then you'll get sort of editing actions and so on. But again, if you've got lots of code on the screen, it's very convenient to not have to go back and forth putting in delimiters. It's very convenient to just select a whole bunch of stuff and say, put a list around that, which we can do right here again. And keep going, more lists. Okay, so a number of changes in 14.3 to icons and tooltips and so on to make things clearer. Something else that's finally there, long requested, is separate British and American spelling dictionaries. So you can decide whether you want color with an O, with just an O or an OU, et cetera, et cetera, et cetera. Things will be tagged appropriately depending on your system preferences. Or you can select the language variant yourself purely in Wolfram language in the notebook system. In case you've been wondering, we've been curating our own spelling dictionaries for years. I personally routinely send in words to add, either because I find them myself using them, or because, well, I just invented them, like words like Rouliad and so on. All right, another topic. We're getting close to the end here. Let's Markdown. So you want a file that's plain text but formatted. So these days, a common way to achieve that is to use Markdown. It's again a long requested feature. So it's a format that both humans and AIs can easily read, and it can be dressed up to have visual formatting. In version 14.3, we're making Markdown an easy to access format in Wolfram notebooks and in Wolfram language in general. So we should say that Markdown isn't even close to being as rich as our standard notebook format, but many key elements of notebooks can still be captured by Markdown. So by the way, our .nb notebook files are like Markdown, actually pure plain text. But since they have to faithfully represent every aspect of notebook content, they're inevitably not as spare and easy to read as Markdown files. Okay, so let's say you have a notebook. Let's get a convenient notebook here. Here's a convenient notebook. Make it a bit bigger here on the screen. So here we have a notebook with some random content in it. And now we want to say of this notebook, we just want to say save as, well, save as Markdown. Oops, save as, not as Wolfram Notebook, but save it as Markdown.md. There we go, Markdown. Oh, I already had one of these, but I'll save it again. Okay, so now this is saved as Markdown. And now let's go ahead and open that Markdown file. So let's go there, and I'm going to double click, and I'm going to get this opening in, I think it's opening in Xcode here. It's opening that as plain text Markdown. So that's this notebook converted to Markdown. I think this Markdown viewer has, what is it, Command-Shift-V, I think. There we go. And that, oh, I guess this had been set to use dark mode by default, and this wasn't using dark mode when I saved that Markdown file. But anyway, this is the Markdown version of this notebook. And you can see that some things are correctly represented, like the headings and so on. Some things, we certainly lose all the lines and so on. We lose the ability, we certainly lose all kinds of ability to resize and so on. We lose lots of the nice features of Wolfram language and Wolfram notebooks, but we keep some things. And for example, here we've also got the default Wolfram language, I think based on language server protocol, syntax coloring for Wolfram language being rendered through Xcode here in Markdown. So the main point is you get to save any notebook in Markdown. It's not completely faithful, but it is a good approximation to the notebook that's useful for many purposes. Okay, let's say you have a Markdown file. Then you can actually select that Markdown file and import it as a notebook. So let's try doing the round trip here. Let's say we say open, and let's say, where was it? The Markdown. Where did I put? Oh, it's not showing because it isn't showing the Markdown file as I have to pick. Oh, right, that's right. I have to pick options for show options. Then I have to pick here that I want to actually show a Markdown file. So there's my Markdown example. Let's double click it. And now that will open as a notebook. It isn't perfect, but that was the result of round tripping through Markdown for this particular notebook. So in addition to using Markdown at a sort of whole file level, you can also use Markdown at a fragment level. So for example, let's imagine that we have let's imagine, what the heck is that? Well, let's imagine that we have I don't know what that was, but let's imagine we have a tabular here. Oh, that was a raw way of generating the tabular. Okay, so now let us go ahead and say this table, say copy as, let's do it for the cell. Copy, oops, cell, copy as Markdown. So now we've got a version of that cell as Markdown, and I wonder we could put it into a text cell here, for example. So there's the Markdown version of that table. Okay, so anything you can do interactively, you can also do programmatically. So I could say, for example, something like this. I could say export as a Markdown string that grid, and now I could say import that this is a string now. Import that string that's as Markdown, and we'll see again it's not completely faithful, but it is getting back the same structure. Actually, we could tell it to import this from Markdown as formatted text, and now what it will do by default in formatted text is it will make that into a tabular object. So another thing, when you have tabular, let's say we can export, sometimes with Markdown, if you're feeding it to an LLM or something like that, you don't want a giant blob of data, you can do a snippet row count. So now it's taking this data and it is exporting as a tabular, as a Markdown object, something which has just snippets here, where it just had a snippet row count. So this is just giving 3 rows in the snippet. Or we could be more elaborate than that, and we could say, give 2 rows at the beginning, 2 rows at the end. Not quite sure. I think it may be grinding through a lot of data to do this. It's a bit surprising it's as slow as this. Well, then there's all kinds of other things you can do. It's all very tricky. You can deal with, for example, let's say we export this lemur to a Markdown file. We could cloud export this lemur, this image of a lemur, to a Markdown file, and we'll get let's say we say system open of this file here, and what we'll see, try and make it bigger. Yeah, what we'll see is that it generated that pointer. It stored a file for the lemur, and then it put into the Markdown a pointer to that lemur PNG. Now, if we did this with cloud export, and we exported a Markdown file to the cloud, we'd have the file as if you asked for that file from the cloud, it would then reference a URL that is the place that it put in the cloud as a cloud object, that it put the image of the lemur. So in this case, that image of the lemur is on my local computer, and if I sent this to somebody else, it wouldn't work. But if I pushed that .md file, if I exported it to the cloud, then in the cloud, the raw PNG file for the lemur would be put as another cloud object that will be accessible to people. All right, we're getting really close to the end. I'll mention a couple of other things. So one thing is something actually related to our web documentation. There is now a sidebar in our web documentation. So if I go to language, no, I want to go to the root guide page. Here it is. And so now if I go to a function like plot, I will see a left sidebar here, which allows me to jump down to basic applications of plot, or to look at look at the documentation for options and so on, go back to scope, labeling and legending, all these kinds of things. It's a convenient way to navigate large documentation pages. I'm sure I can make it a bit narrower here. And this is a case where we have a very large number of options, so it's kind of open by default. You can close up all those intermediate options by clicking on that. Kind of a different version of something like a cell opener. So that's pretty much the story. It's a lot of stuff in version 14.3. There are a bunch of other things that we've added. We've added video stabilization. We've added AVIF files for importing images. We've added, in speech synthesis, we've added the ability to do all speech synthesis locally. We've added some things to do with the final last tail, I hope, of dates, adding new day types like non-holiday and weekend holiday to deal with day matching in dates. And we've added features to make it easier to select dates in tabular objects. We've added things in random tree to make one able to label random trees more easily. We've added bit vector support in data structure using multi-threading, and also functions like pick can now operate on bit vectors efficiently. We've added in GPU array objects, we've added support for some new functions like unit step and numerical sort. In partial differential equations, we always have a new thing in partial differential equations. In 14.3, we've added the option for solving axisymmetric fluid flow. So you can compute, like here's a fine picture of flow through a pipe that was computed using axisymmetric fluid flow. We've added some new features for chemical formulas and so on, new databases for accessing protein folding capabilities, or rather for accessing structure of folded proteins. Then, well, there's some new features of the compiler, somewhat technical but useful, for the function current compiled function data to provide introspection on compiled functions. So if you're inside a compiled function, you can figure out things like what type you're dealing with within that function. There's a whole bunch of subtlety to do with calling back from the compiler to the core Wolfram language system, and we've added some things for that as well. Well, okay, that's pretty much it, folks. That's 14.3. It's a 0.1 release, but it's a pretty big 0.1 release. A lot of long requested features. I'm excited about them. I've been waiting for some of these things for, well, some of them for 38 years, 37 years. So they're finally here. And I hope people will find them really useful. And I think lots of additional polish added, just making Wolfram language easier, smoother to use. Don't forget, if it seems difficult to remember all of these different capabilities that we now have, use Notebook Assistant. It's your friend. You can ask it incredibly vague things, and it will tell you specific Wolfram language capabilities and help you figure out how you can use them. Well, so I think that's all I had to say, other than download this. If you're at an organization with a site license, it should be being updated there. You can or you can download it directly from our website to get, for all platforms, the latest version for the desktop. Or you can also run version 14.3 in the Wolfram Cloud. It's usually the case that just a few days before we release a version, secretly the cloud starts running the new version. But it's right now, if you go to the cloud, you will be running version 14.3. So enjoy version 14.3. It's the result of a lot of R&D that we've done. Some of it has happened right within the last 6 months since we released version 14.2, but some of it has been going for a long time. Sometimes in a few cases of a few things we've added, we've been at least thinking about these things for decades. and they're now here in version 14.3. So enjoy the new release, and look forward to talking to you another time. Bye for now.